Hello everyone! In this video we will continue to examine topic 5.4, the magnetic effect of electric currents, and in particular we will continue to consider magnetic fields due to different current arrangements. So, in the last video we discussed sort of the essence of how to figure out what the field structure due to a long straight current carrying wire was. We introduced or have seen the right-hand rule, and we saw that the field loops around that wire in concentric circles with decreasing strength as you move away from it, according to the right-hand rule, where your thumb is in the direction of the current, thumb of your right hand that is, and your fingers loop around the wire accordingly. So, consider what happens if you simply have a loop of current carrying wire. So you take that long straight wire and you set it up so that there's a straight loop. In the ideal case, this is just a loop of current that goes around in this direction. Notice this is impossible in reality, at least under normal circumstances. But for now, just consider what the magnetic field would look like. Well, apply the right-hand rule to each part of the loop. You put your thumb in the direction of the current, and your fingers of your right hand loop in on this side and back out again on the outside. You do that here and get the same result here, the same result always in and out. Okay. So what happens is the magnetic field produced by all parts of the single loop reinforce in the same direction inside the loop of wire, and are in the same direction outside the loop of wire, but are much weaker. In reality, to make this sort of loop structure here, what you're going to do is run a long straight wire sort of up and around in a loop-to-loop. But the effect is the same. Strong field in the appropriate direction inside the wire where those the field contribution of the different wires themselves add up, and slightly weaker field on the outside of the wire in the opposite direction. So what happens if you sort of turn the loop and look at it from the side? All right, well, now we're drawing the current at the top going into the page, and the current at the bottom of the loop coming out of the page. So this is sort of the cross-section of one side of the wire, and this is the cross-section of the other side of the wire. What we can see is that if we draw our field lines, they wrap around one side of the wire, they wrap around in this direction, and then coming out. If your thumb is coming out of the page, the field lines will wrap around in this side. What you can see is that the field inside is stronger. It's reinforced on both sides here, and weaker on the outside. It goes in the same direction one way through the loop, and then curls back around on the outside of the loop. And big picture, okay, so that was sort of our first ingredient here. But what happens if you use many, many loops, okay? Well, if you use many loops, you get this structure called a solenoid. Okay, a solenoid is the term for a bit of wire that loops around and around and around and around and around in the same direction. And you run the current through it and take a look at what you get. Well, the current in this particular diagram is always going to go up the near side and down the far side. Notice that that's true for every single loop. And the field produced by those loops are going to reinforce. So it goes up the near side, down the far side, up the near side, down the far side, and so on and so forth. As a result, the field from every single one of these loops adds up and produces the field as shown right here. This is the field due to a solenoid. So it's going to go sort of using that right-hand rule for any given loop, right? It's going to send your field through all of those loops, and then it'll curl back around. Notice that this field pattern looks basically identical to a bar magnet. You could even label the quote-unquote north end and the quote-unquote south end, although it is becoming increasingly clear that a North Pole, South Pole concept is not getting at the essence of what's happening here. Now, what's happening are these closed magnetic field loop lines. And notice that the magnetic field inside the solenoid is strong, it's reinforced, and it's approximately uniform along the length of the solenoid. For that long, thin solenoid, if it's infinitely long, it turns out it is uniform. But for a real-life solenoid, it's approximately uniform inside the coils of wire. This is very, very similar to a dipole or a bar magnet. Inside that long, thin solenoid, you could calculate the magnetic field. This equation is not assessed in the IB, but using some more advanced mathematics, you can derive that the magnetic field inside the solenoid is approximately equal to the permeability of the material inside it. So if it's an empty solenoid, the permeability of free space or of air times the number of turns times the current through the loops. So that magnetic field is proportional to the number of turns, the current strength, and the permeability of the material inside it. Okay. Notice that mu is equal to mu zero in a vacuum. This particular equation will not be assessed in the IB, but you do need to explain the relationship between, or to know the relationship between the number of turns, the current, and the permeability for the magnetic field due to a magnet. And notice this expression refers only to the magnetic field inside the solenoid itself, which is approximately uniform.